In this final lecture about penalized regression, I will discuss how to apply it to econometric applications and to classification. The main difference with applying the lasso in econometrics is not so much the lasso itself, it's broader in terms of the theory, the DGP assumptions that we've been making so far. And then of course the question is, if we change those DGP assumptions to something that is realistic in econometrics, do we still have all these nice theoretical properties? Which of course translates to, does it still work as well in practice? Well, we should of course first think about what is unrealistic. Clearly fixed design is very unrealistic in almost any econometric application. We hardly ever have variables which can be deemed as fixed, except maybe for some experiments where the researcher controls the covariates. So of course we also looked at random design, that's a pretty standard assumption, but still random design in its basic form means that everything is IID, which is also still very restrictive for most econometric applications. Just think about time series models, for instance. Well, then most of the theory relies actually on normality of error terms, and if not normality, then at least it's something which has as thin tails as the normal distribution. So this is definitely not realistic, given that in many forms of economic models we have fat tails or outliers, heteroscedasticity, you name it. Now, thankfully there has been quite a lot of extensions of the lasso to econometric settings, so it's become really popular in recent years. And what I will briefly cover is two strands of applications. First is more microeconometrics, where people focus on estimating treatment effect or related causal effects, using, for instance, instrumental variables, dealing with issues such as heteroscedasticity, but typically still not dependence, which is in the more macroeconometric settings. In the time series world, of course, a much bigger issue. So here people look at serial correlation first and foremost, but also fat tails. Think about applying it to financial data, for instance, and heteroscedasticity, of course, as well. So if we focus on the more microeconometric settings, then there are a lot of papers by a professor from MIT called Viktor Chernozyukov and his group of co-authors who have basically established the theory of the lasso and variations for these kind of cross-sectional or panel data-like models. Now they do something which is different than the standard setup, and that is they say, well, let's not assume a linear model from the start. Let's assume we have some sort of model where we have covariates, predictors Z, and we have Y being just some function f of those covariates, plus of course an error term. And this f is an unknown function, so we actually don't know the particular functional form. So this makes this a very general model. Now, of course, there's no direct link to estimating linear models with the lasso. So what they argue is, well, you can probably come up with a linear model that is a nice approximation to this model. And in particular, what you can do is you can transform your z's into new regressants, x. And these transformations can take any form, but you can think, for instance, suppose that you assume f is a smooth function, you could approximate that using a polynomial approximation. So these transformations could involve, for instance, polynomials of x. Now, of course, there are many other choices possible, and it really depends on the kind of setting that you're looking at, what you think is appropriate. And now, of course, what we can do is we can not just look only at x and x squared, but we can look at x to the power 3, 4, 5, and so on. And we can also look at various different transformations. So even if your z being k-dimensional vector with k not necessarily large, so even in the setting where actually z is small, you could still have a large p-dimensional x coming just from this z. Of course, you could also already have a high dimensional Z to start with. And this comes back to what I mentioned before when we see linear models as approximations to the truth. And high dimensionality is something that comes out because, well, think again about Taylor expansion of smooth functions. The approximation gets better if you include more terms. So high dimensionality naturally arises in this kind of framework. So they make this formal and they then say, well, let's, instead of writing y as f of x, of f of z plus epsilon, let's write it as beta prime x plus some residual, some approximation error, which is f of z minus beta prime x. And so what they then assume is that there exists a sparse beta that makes this approximation error small. Small being small enough to essentially ignore it while still having, that still allows you to have good estimation properties of your model. And they show that if that condition holds, and of course whether that condition holds really depends on each particular choice of combination of f and the x's that you get, then they show that the lasso actually still works as well as before. And then they start relaxing it. They say, well, let's assume non-normality for your epsilons. Let's assume heteroscedasticity for your epsilons, and it still works well. So this is actually a very nice setting where we say, okay, we move away from the linear model as the truth, and instead see it as an approximation. Of course, you still need to argue that this is a good approximation, but that is something that, depending on the application and your economic model that you have, you can do. But if we assume that it is indeed a reasonable approximation, then non-normality, heteroscedasticity, they actually do not affect the lasso. And for instance, what they apply it to is instrumental variables estimation, where you could have a large set of possible instruments, right? So you have some variable of interest that you know is endogenous, but you don't have one clear instrumental variable for it. You have a large set of candidates, but you can use the lasso to select the right instruments from this large set of candidates. Another thing that they look at is treatment effect models where we have a large set of controls. So we are interested in the coefficient of one particular variable, our treatment, and we have a large set of controls to ensure that actually we do have exogeneity. Well, they show that you can then also efficiently use the lasso to select the relevant controls from that. And they, in particular, what is in particular interesting about these applications, what they look at is not just applying the lasso of estimation, but they will also look at inference. So we will be coming back to these models, particularly this treatment effect model. We will be coming back to that in the last part of the course, where we really focus on doing inference. Now, of course, as I said, you can also apply it in time series. So, well, you might notice I replaced the I index here with a T, just for fun to indicate that this is a time series. And assuming you have still a linear model, whether it's a true model or an approximation, in time series setup, and well, if you would have these kind of models in time series, things that you have is that typically in X you would have lags of Y, you would have also probably lags of other X's. There would be serial dependence among the X's. There may even be serial dependence among the epsilons, although of course you would not want to have both lags of Y and serial dependence there. But you would definitely also want to have is something like non-normality, effect tails, heteroscedasticity. You think, for instance, about you want to have a guard structure, right? Maybe you want to estimate such a model on financial data. And what they show in this paper, and also several others have extended that, and what we see in general is that the lasso, and if you focus on variable selection consistency, the adaptive lasso, that it does actually still work. And you also, in terms of regular consistency, we still have these results. Now, the main thing that this set of papers shows that we need to be careful with is the distribution over epsilon. So if we move away from normality and we move away from nice distributions which have thin tails, then actually what this has, the effect that this has is it has an effect on how large P may be. So in particular, if we don't have exponential decay of the tails, but we have polynomial decay, meaning that actually not all moments exist, so you have only a limited number of moments of your epsilon, then in that case P may also grow only polynomially rather than almost exponentially. So that also means that if you have these epsilons which are not these nice normally distributed random variables, but they have, I don't know, they have a t distribution with just a few degrees of freedom, then you would not want to use, if you have just 50 observations, you would not want to make P equal to 1000. Instead, you would want to make P somewhat, allow it to be somewhat similar to N, but not that much larger. And of course, it depends on how fat the tails are, so how few moments exist, how slow or fast P may grow. And in a way, of course, it also makes sense. I mean, if you have these epsilons which have outliers or just take large values, it makes life much harder to pick out the relevant variables and do your lasso estimation. And therefore, we have to make some concessions, and that means not apply it to too large data sets in terms of the dimension P relative to N. So one particular application where the lasso can be very useful is vector autoregressive models, VAR models. Right, take a VAR model of order K. VAR models just says that we have a vector of time series, so not just one, but d of them, and they depend on the lags of all the other time series, and of course also on its own time series. And they depend in particular on up to k lags. So every AJ is a matrix of dimension d times d, indicating how all the d lags at time j affect all the d variables at time t. So we have d squared number of parameters in here. We have an additional k lags, so we have k times d squared parameters in total. Well, this of course very quickly becomes high dimensional. In particular, if you think about where these VAR models are often applied in macroeconomics, their n is not very large. If we have, for instance, we have often no more than quarterly data in macro, and well, if you have 50 years of data, that's already very large amount of data. So you would have, in that case, you would have an n equal to 200. Well, just take let's take 5 variables, which is not a lot in your series, and you have 4 lags. Right? So it depends on observations within the last year, which is definitely not unreasonable. Then already you have 5 squared, 25 times 4 is 100 parameters to estimate. So it very quickly becomes high dimensional, and this is why in practice in standard VAR models, but also in their non-stationary variants like VAC-M models, you typically only see models estimated with 3 or 4 or maybe 5 variables. You will not very quickly see a VAR model being estimated with 10 or more variables, even though you typically would want to do that. If you think about macro, it's not hard to come up with a case where there are definitely 10 or more relevant variables you would want to put in your VAR. So the lasso really is a very natural way to proceed here. And indeed, many people have looked at it. So there's one paper by Koch and Caillot which sort of started this off. You can find the link on the course page. And it shows that actually lasso can be applied very successfully in these VAR models. Now, there's a whole list of economic applications. I mean, it doesn't make much sense to discuss them all in this lecture. Instead, go on Canvas, go on the course page, and have a look at your assignment, the page for the paper, because there's a whole list with suggestions of different kind of economic, but also somewhat beyond economics applications that you might want to have a look at. For instance, if you decide what you want to work on for your paper. Now let me look at another kind of extension, which is not per se only econometrics, but it's also important to do something beyond just linear modeling. In particular, I want to look at the binary classification model. So I already introduced that. So it's the model where our outcome, y, is just ones or zeros. So we just have two classes that it can take. And we typically model that by saying, well, there is some linear combination of our regressors which determines whether we observe a 1 or a 0. So you would typically say that your beta prime xi plus some error term epsilon, if that's larger than 0, you get a 1, if not, you get a 0. Now what we typically do is we say, well, there you could also say that do it in terms of a latent variable y star, so some variable you actually don't observe, and this variable is linear in x, but we only observe if it's larger than 0 or smaller than 0, because if it's larger than 0, then y will become 1. If it's smaller or equal to 0, y will become 0. Well, we can model this by modeling the probability that we observe a 1, conditional on the x's, on the regressors. And we can simply then write out that that probability is actually equal to the distribution of your epsilons evaluated at the point beta prime xi. So what we typically do to solve that problem is assume a parametric distribution for f, because in that case we can do maximum likelihood estimation. Right, so we write down the log likelihood and then solve for the beta that maximizes that log likelihood. Well, in this particular case, our log likelihood is very simple because it's the product of the probability that that particular y is actually 1 or 0, and that thing just has a Bernoulli distribution. And the probability that it's 1 is of course just equal, as we saw here, to f of beta prime x. So it's just f to the power y times 1 minus f to the power 1 minus y. And we can of course then write that out. And then of course it depends on how we choose f. Right? Do we choose the normal distribution, then we get the probit model? Do we choose the logistic distribution, we get the logit model? Or in fact, as people typically call it in statistics, it's called logistic regression. Well, and of course you can plug in and you can write down the likelihood and so on. And this typically would then have to solve numerically. Now, so far there was no lasso involved, but of course we can just use the lasso in this case as well. So you can add a penalty term to the likelihood. So typically if we want, given that we are thinking then in terms of minimizing, so we multiply the log likelihood by -1, then we can add plus lambda times a penalty term. So if you take q equals to 1, the lasso, you just get the absolute value of the elements in beta. So take for instance logistic regression with the lasso penalty, you would look at this objective function that you want to minimize. And well, there's not that much new, because we can, for many of these cases, actually just use coordinate descent to find the solution. And so in fact, the lasso or more general penalized regression is something that is you can definitely use beyond linear models. So for instance here for classification. But in fact you can do that for any maximum likelihood estimator. I mean, the formula given here is entirely general. So you could do that for whatever kind of maximum likelihood estimation that you want. And you can even move beyond maximum likelihood estimation. You can also look at just generalized linear models. So what we of course need is this linear structure in beta prime xi. That should be linear. But apart from that, you can put that in then into a nonlinear model. So that really extends the generality of the lasso quite a lot. And so in fact, for instance, what you'll see in GLMNet, the very popular R package for lasso, there are several models, including the logistic regression, that are actually already built in there. So that brings us to the end of the part for the lasso. And even though we can, of course, could extend that a lot and discuss all sorts of extensions still, we should always realize that we've worked on the assumption that beta was sparse. So many of the elements of beta were actually zero, or at least close enough to zero that it did not hurt us to actually leave them out. And this might not always be something that everyone wants to work under. So there are people who get very uncomfortable working under sparsity. In particular, people in economics, they get even more uncomfortable with that. Now, it's not the end necessarily to the lasso, because there are ways we could extend it by looking at different sorts of sparsity. So for instance, does it seem reasonable to assume that many coefficients are actually equal? Well, if you could do that, then what you would have is not sparsity in beta, but sparsity in the differences between coefficients in beta. And that actually brings us to what is called the generalized lasso, where we don't necessarily assume that beta is sparse, but we assume that some linear combination of beta is sparse. And this, for instance, is a setting where this would occur very naturally in economics if you look at panel data settings, where you would allow for some heterogeneity across different units, but not too much. You would expect that actually many of the coefficients are equal. So you could apply this sort of generalized lasso to that kind of a problem, where that would allow you to find clusters, right? Groups where coefficients are equal and other groups where they are not equal, instead of finding the relevant and irrelevant coefficients. And so there is one particular extension, the so-called fused lasso, which looks at equality of coefficients, which is become a very popular method as well. Now, I don't have the time to discuss that in all its details. If you go to Canvas, you will find reading material if you're interested in this kind of applications of the generalized lasso. But that still has its limits, because assuming that, for instance, the betas are all similar is still not always going to be very helpful, and people might still be uncomfortable. So take, for instance, a typical macroeconomic thing where we want to forecast gross domestic product, and we have a whole bunch of macroeconomic variables. Well, is sparsity realistic there? Is it realistic that all of these variables that we consider do not impact GDP? Because that's what you would be saying, or at least you can leave them out. But if you look at big data sets and macro, I mean, it's likely that all of these things matter. I mean, some of them even are just components of GDP. So you could have sectorial data, for instance, where it's very hard to say, well, one particular sector actually is relevant, but the others are not for GDP. So this is something that people in economics don't always want to work under. Well, you can of course extend that to generalized lasso, but you remain with very similar problems there. So what we will do in the next part of the course is we'll look at an alternative way to impose structure. So we will not be looking at the betas directly anymore, but we're looking instead at x's, the variables, and assume that they are generated by some commonalities. In particular, we call these things common factors. So, and these factor models provide an alternative way to impose structure on our model. And whereas penalized regression comes more from the side of statistics, factor models in the applications kind of way that we consider them are really more econometric tool. So the next lectures will discuss those models in more detail. And of course, we'll also go back, wherever it's necessary, go back to penalized regression to make a comparison and look at the differences and similarities between these methods.